Okay, welcome to week 7 of CNTR 1341. Sorry, I haven't updated this slide. Fundamentals of PLCs. Last week we covered. Sorry, what did we cover last week? I only have my notes up. Last week we covered Ethernet and networking. Does anybody have any questions about last week? There's a quiz. I haven't gone through it to see how people have done. But did anybody play around with ping on their local network? Solve any networking problems? Become the computer guy at work? Nothing that drastic. Let's see here. All right. All right, everyone did good. Everyone passed. So I'll look at those and I'll send some feedback. If there's no questions, we'll dig into week 7. You do networking stuff at work. Yeah, you're good. So last week you were probably just like, oh, this is great. Learn this again. Did I get anything wrong, Tatiana?
What do you mean?
Did I get anything wrong about the network?
No.
It's when you get into computer networking, it's one of those fields where you learn some and you think you know computer networking, and then all of a sudden you'll attend another course and you're like, holy crap, there's way more.
I learned something new. I learned something new too, actually.
That's excellent.
Yeah, thank you.
I'm glad to hear that. I'm glad to hear everyone's getting something from this. But yeah, computer networking it's one of those like Russian nesting dolls where like you understand something, you dig in a little further, and then all of a sudden there's math, there's entire industries that are all about network security, firewalls, DMZs. You can spend your entire career on only setting up networks, and they're very desirable and very well paid positions because there are so many things. And one of the big issues with networks is that's everyone's probably heard of ransomware and hackers penetrating networks. When you're building networks for your profession, you have to build them, and you constantly have to upgrade, and you constantly have to develop your skills, because you always have to have the best equipment, the best setup. When you're being attacked, when your network is one that's desirable to get into, whether it's to steal information or ransomware, the attackers only really need to be at the top of their game once, and it is constantly a changing field. So if last week, for whatever, if that piqued your interest and something you want to learn more about, you can spend the rest of your career on networking, and it's really neat stuff. It's all neat. Everything is neat about programming and PLCs. Okay, so this week we're gonna pivot. Sorry, I lost my notes. Here we go. We're gonna work on some electrical panel design, electrical drawing review. This week and next week are kind of combined together. We're gonna review some electrical drawings this week. Next week, we're gonna go over some more electrical drawings, and then we're gonna get into what are called shop drawings. And then there's going to be a group assignment next week. So if anybody knows that you won't be able to attend in class next week, let me know, because I do need to split you guys out into um, hopefully equal sized groups, but I don't want to throw 3 people who aren't going to be here for sure next week in the same group. So send me a private message or an email if you know you won't be here, and that will help me out. So this week we're going to cover NEMA and IEC. These are standards for drawings. They're also standards for equipment, depending on what industry you're in. You've probably seen these, especially the guy, I think is it Scott, you're in the panel shop? You guys build panels, you probably see NEMA, everything all the time. IEC is more of an international standard. So most of the stuff you're going to see in North America is going to be in NEMA codes. We'll cover some of that. We're going to get into some electrical basics. So I apologize to the electricians and the electrical engineering students if this is a very basic refresher. We're going to learn about voltage, current, resistance, how they relate to electrical drawings, and some of the things that you need to watch for when you see electrical drawings. We're going to look at how to identify various electrical symbols on drawings. We're going to look at how to read single line electrical drawings. And I'll show you a number of examples that I have permission to from some previous clients of mine. So you'll be able to see a bunch of different facilities, primarily water and wastewater, but lots of drawings. Then how to assign and read and understand electrical drawing number lines. Reading electrical drawings is a little different than reading mechanical drawings, especially when you get into control panels. If you're going to spend any time with PLCs, you're going to be in and out of control panels all the time. So you need to learn how to read these drawings, and it is a developed skill. And the more you see, the more you'll be able to identify, but they're good. We'll work through it. Oh, there's everyone. Let me just finish the attendance here. Right, IEC versus NEMA. So NEMA stands for National Electrical Manufacturers Association. And NEMA power drawings, they look something like this. This is a pretty bare bones example of what a motor starter circuit would look like, where you've got your power circuit, line 1, line 2, line 3, a motor starter, T1 and T2 here for your overload relays, T1, T2, T3. This is your motor. And then you've got your control circuit down below, stop button, start, your motor, an overload, normally close contact of that overload, and then your seal-in circuit. IEC is the International Electrotechnical Commission. So again, it's more of an international standard. So if you are doing work, you end up working on Schneider PLCs, Siemens PLCs, panels that are built in other countries. If you start doing work in other countries, the EU, Germany, Asia, you'll see a lot of the international drawings. So you'll notice where the NEMA one is left to right, top to bottom. The IEC standards are top to bottom, left to right. For the most part, they do kind of they will have some left to right wiring. They'll show parallel circuits to the right, but this is the general layout of the two different standards. So again, NEMA is typically used in North America. Drawings are read from left to right. And then NEMA equipment is typically more rugged. I say typically because it's kind of hard to judge based on the drawings. That's more of the actual physical equipment. NEMA equipment is typically larger. When it comes to electrical equipment, there's not a lot of moving parts. So when you size things up electrically, they typically have higher electrical ratings, EMP ratings, different things like that. IEC, typically used outside of North America, like I was saying. Drawings are read top to bottom. IEC equipment is typically less expensive because when you size things up, especially for electrical, you're adding more copper, you're adding more metals, precious metals to them. So they cost more. And typically this equipment is more compact. So one of the things that you have to contend with when you're looking at IEC rated equipment versus NEMA rated equipment is some of them wouldn't pass spec in different countries, if that makes sense. You can get some things that'll be fine for the EU and follow IEC standard, but if it doesn't meet CSA, it can't go in Canada. That's something that we can cover later. Are there any questions about drawings? Most of the drawings I have seen in North America, provided by engineers, provided by panel builders, are this NEMA left to right, top to bottom standard. The IEC standard, the only place I've seen it has been a large windmill and solar farm I was doing work at, and they had Samsung wind turbines and a whole bunch of Siemens products for the inverters for the solar farm. So everything was built and supplied from Samsung, I believe, is Japan, and the Siemens equipment is all Germany. So everything was coming out of the EU and Japan. So it's all IEC. Any questions? Again, there's nothing wrong with one or the other, and the basic flow of the diagrams are the same, but you will notice here that there are differences in the symbols. The more, again, the more you read, the more you'll notice. It's a developed skill. So some basic electrical principles. Everybody who's done any sort of electronics program knows this calculation. V equals I times R. Voltage is V, current is I, and R is resistance. The other equation of the power triangle, as they put it, is I equals V over R. This is the universal calculations that you need to know, because when you're checking drawings, it's very important to be able to quickly confirm if your equipment is sized properly. Do you have the right breakers for the circuit that you're looking at, especially if you're in an engineering environment where you're building panels, you're supplying fusing, you're supplying protection equipment for specific pieces of equipment. It's important to know what the voltage is that they're using, what's the resistance, what's the rating of those parts, what's the current that we need to protect it with. So when you're sizing your breakers or your fuses, you want to make sure that you're not putting in a fuse that's 10 times what's going to be drawn, because it's far better to size it properly and blow a $5 fuse than damage a $10,000 piece of equipment. So very basic stuff. And again, if you've done electrical stuff before, I'm sorry I'm repeating this, but imagine an electrical circuit like this bucket of water. This bucket of water is analogous to a battery. So right now, you have a bucket of water that has a bunch of potential energy inside of it, which is it's just holding the water, just like you would have here a 24-volt battery. It has potential energy in it. So with no water flowing out of the bucket, this is similar to an open circuit battery. There's no current. The battery isn't connected to anything on the left. There's no current flow. So if we connect a circuit to the battery and make a hole in the bucket, this will make sense for those who are thinking I'm crazy. What we're showing here on the left is we have a 24-volt circuit, and we've added in a resistor, whether this is a resistor or a heater or a device that just has resistance in the line, is again comparable to putting a hole in the bucket. So if you have a 100 ohm resistor on a 24-volt circuit, and you do the math of current equals voltage divided by resistance, you get 0.24 amps or 240 milliamps for this circuit. So you have a high resistance and a low current. So the analogy here is that the high resistance is a small hole, allows a small amount of water out. Oh, I clicked on the wrong thing on my other monitor here, sorry. So if we changed the resistance, so we now have smaller, lower resistance on this resistor, it's like putting a larger hole in the bucket. So with this resistor on the circuit, we calculate at 0.615 amps or 615 milliamps. It's like a larger hole in the bucket, less resistance, more current. Larger hole, less resistance to holding the water in, more water spills out. We have 10 amps, an even bigger hole, as you can guess, and the math is pretty easy for that one, divided by 10, 2.4 amps or 2400 milliamps, large hole, bucket's empty, battery's drained, more current is used. So in this, when you know the current, you can then fuse this properly if you know that there is a limit that this device can take, or there's a limit on another device in the circuit. And this is the last of the electrical theory. This is the only math, but does anybody have any questions? This is really, I don't want to say basic stuff. If you've never seen it, it might be confusing. Any questions? No, all right, perfect. So does it, I'm just gonna move on. We'll get back to that. So electrical drawings. So electrical drawings are comprised of electrical symbols. There are different symbols for different devices. We've seen some of these drawings already. This example here is a motor starter on a 3-phase line. The symbols typically define the connections between electrical devices, and they're normally representative. So they're not going to be super detailed. You won't show in your electrical drawing typically every single terminal block, every single nut and bolt. These aren't mechanical drawings like you would get if you were a fabrication shop needing to actually manufacture the pump to assemble it. The electrical drawings that you're typically going to use or be seeing for PLC engineering work are going to be, you're going to have your 600 volt, you're supplying 600 volt to a motor. The motor, you might have your horsepower or kilowatt rating. And then you'll have your control circuits. It would be far more detailed drawings that would get down to individual connection points. Here's an example of, sorry. So again, representative, any questions while I'm just going to keep going. It'll make sense later. So this is an electrical drawing showing what would sometimes be called a lighting panel or a lighting schedule or a fuse panel, breaker panel. What you have here at the top are, this section is showing that you have emergency lighting connected to fusing. There's a 15 amp fuse connected to these emergency lights. On this side, you've got 15 amp fuses connecting to these reservoir lights. They'll show the amperage and again, the devices that they're being supplied to. At the top here, this is a circuit breaker or a switch being shown that it has a linkage between them. So when this switch is thrown, both of these will open and close at the same time, where these ones, since they're fuses, this is kind of confusing because this could also be construed as a breaker, but these ones are actually fuses. Again, just indicating that this is a single fuse supplying this lighting. The center here is showing the interconnection between the different phases. So here you would have one phase coming into this panel and a second phase coming into this panel. But the important thing to look at on this type of drawing are these dots. So where there's a dot, it indicates a connection point, but where there's no dot, it implies that there's a pass through. So for this particular panel, this phase supplies power to these two devices, where the other phase, because of this connection, supplies power to those two. So again, it's representative of where the power's flowing, but is not a mechanical drawing of what might be a lighting panel or a fuse block or a fuse panel. Are there any questions about this? Again, we're going to have more drawings to look at too. Okay. So instruments. So instruments are typically shown with a circle with a letter in it. A here be an amp meter. Connections to other instruments are single lines that look like lines coming in and out. These also indicate wire. So this could be, there could be a note on this telling you that this is red wire 16 gauge AWG, which just would specify the color of the plastic or coating on the wire, the amount of copper and what the copper is consisted of, whether it's solid core or if it's stranded wire. P&ID electrical symbols, that's correct. We can get to those. There are lots of other letters that you'll come to, and the important thing to realize is that although there are some standards out there, P&ID, there are some IEC and I can't think of the acronym for the Automation Society. ISA has some standards for P&ID drawings. It's important to know that these symbols might change based on the country that you're in, based on even the company that's supplying them. And you always have to look for the drawings that you have. There's going to be a legend in there that will tell you what the different symbols mean for that specific project. So, for example, you could have an A for an amp meter, kW for a kilowatt meter, V for volts, HZ for frequency, which would be the speed of drives, PF power factor, and there could be many more. As you run out of characters, the more devices that you have, there's only so many 2-letter character combinations you can get. So you'll see some that'll have numbers. Depending on the drawing that you have, you just have to pay attention to what they are meaning. So again, the letters listed above will not be identical between all regions or countries. Always look at the legends for the drawings that you have. And I will show you some examples of legends. I can even pull up some, I'm going to have some P&ID drawings to show you process P and ID. So process and instrumentation drawings are a little different than some of the electrical stuff that we're getting into. And I'll show you examples of those as well. For the assignment next week, I'm pretty sure it's just electrical drawings. So powering up equipment inside of a control panel, PLC IO drawings, and then we're gonna get into some shop drawings as well. So lights. So lights, like devices, there's a circle, only the lights will have some sort of indication, these 45-degree lines attached to it for NEMA drawings. I've seen some lights that will actually have, sorry, I'm just gonna pull up my pen thingy. So like draw. I've seen some lights that'll actually look like this, or they'll actually draw a light to represent a light. Typically, the inside of these lights, depending on what the letter is, will indicate either its function or the color of the light. So the connections between it and other lights are also going to be wires. You could also have jumpers, but it's some sort of electrical connection. R here stands for red light. F here could stand for fault. The letter in the center is either the type or the color of the light. Again, check the legend or check notes in the drawings. Off to the right of the drawing, typically there'll be a description as to what's going on. G here could denote, again, notes. Electrical drawing note lights are type G, push to test. Type G, who knows what that means? There's probably going to be a list or another note elsewhere that says what type G are. So some more general symbols that you're going to see. Resistors. So resistors are typically generic current limiting devices, heaters, anything that creates a resistance that they don't have a specific symbol for. Fuses. So here's an example of a fuse. We saw another one before that had the box across with that kind of bump on the top of it. So fuses are cheap. They are overcurrent protection. They're typically very fast to blow, and by blow, they will sometimes explode, but a fuse is a physical wire running between two ends called a filament. When too much current passes through that filament, it'll heat up and melt. It's like a light bulb, only the filament is designed to break. We'll have circuit breakers. So here, because there's no tube between the center, you know that this is a circuit breaker. They're also overprotection current. They typically take longer to open, and by longer, I mean like fractions of a second. You can get some fuses that'll blow in milliseconds, and a circuit breaker could take 100 milliseconds to trip. And sometimes that difference is enough to protect or burn out your very expensive piece of equipment later on down the circuit. Again, typically slower than fuses, but circuit breakers are resettable unless they are hit with a voltage so much higher than they're rated for that they just blow up, fuse open or fuse shut. But they're very convenient. Most houses nowadays have circuit breakers. The idea behind them for electrical control panels is identical. So transformers, these are used for converting AC voltages. This is typically what they're going to look like. You have here a primary side, H1 and H2, and your secondary side, X1 and X2. These could also be primary voltage or high side, low side. This one, almost always, there's going to be notes beside it detailing your incoming voltage, your outgoing voltage. The transformer might have information on whether it's oil cooled, air cooled, the type of oil, whether or not the windings, there's different windings for different voltages. But they'll all typically look like this and maybe have additional grounding beside it. Capacitors. So capacitors are like little batteries. They will charge up and then release their power over time. They are measured in farads, typically microfarads. Whole farad capacitors are huge. Most of the capacitors that we're going to see are going to be microfarads. I think I held a 1 farad capacitor. It was the size of a 2-liter pop bottle. Most of the ones that we're dealing with are very small inside these electrical cabinets, unless you're dealing with oil and gas or high voltage power generation equipment. And then grounding. So these are the two symbols you'll see for grounding most of the time. Sometimes they're interchangeable. Other times, depending on your project, they may not be. Grounding is important for electrical circuits to prevent surges. You need a place for shorts, surges to go to ground. But when you get into some complicated control equipment, analog signals, sometimes you need to have separate grounds. So you do have to pay attention to building ground versus earth ground versus isolated grounds. This is something that you will have to pick up as you go, and you'll have to know about your specific project. If you're dealing with high voltage equipment that's being installed inside of electrically shielded like e-house, typically they're called e-houses. They will have their own grounding grid that will be isolated from electrical ground. So then there could be different grounds. There could be grounds with a triangle, grounds with an exclamation point to delineate which ground is which. So again, always look at the legend for the project that you're working on. We've covered these already. These are push buttons. So we've got a normally open, a normally closed push button. So a normally open push button, when not pressed, is a disconnected circuit. The normally closed push button, when not pressed, is a connected circuit. When you press them, they will either open or close their circuit respectively. Normally closed, normally for stop buttons or fault signals. Well, these are buttons, so not fault signals, but these are stop buttons. These ones would be start buttons, typically. Then contacts. So these you'll find contacts on almost all pieces of equipment when we're dealing with PLCs. So these look like, if you remember from any of the ladder logic we were looking at and some of the other drawings, this would be a normally open contact, and this would be a normally closed contact. You're going to find these on relays. You're going to find these on overload contactors, pump starters, any piece of equipment that might have a fault or a status that's going to come back to be wired to a PLC will have a contact of some sort. Typically, you could have ones that have normally open and normally closed, which we call Form C, but that's going a little too far. Yeah, you just need to recognize for inside the drawings, which are normally open, which are normally closed. Okay. And then these will typically change state based on something external to these contacts. So when you see a push button like this, the action on this push button will be depressing the button, or if it's a limit switch, the limit will be reached, where these contacts, they'll be connected to something else. So when a device runs, so if you've got a motor starter, the motor starter is going to have an auxiliary contact. When that coil is pulled in, oh, losing twice. When the control circuit tells the coil to pull in, it'll pull in, the device will start, the external run contact will go from an open state to a closed state. It could be a fault contact. If you've got a level transmitter that has an analog, but also has, if it's an ultrasonic, there's a fault indicating that it's ultrasonic transmitters not working properly. You could have a contact that indicates that coming back to the PLC. Any questions? Okay, so let's investigate station 100 E101. You don't have this drawing yet. You'll get this drawing next week. I'm going to overview some of the stuff that you'll see on them, and then I'm going to open up a whole bunch of drawings to show you guys. And hopefully, if I'm going too fast, once I get the drawings open, let me know. I'm going to try to step through them very slowly. So again, everything here is on these drawings have been simplified to get kind of not the point across, but when you look at these electrical drawings, even when you get professional electrical drawings like this that say you're wiring up a transformer, you're wiring up a level transmitter, you always have to look and go and find that piece of equipment's manual. So that manual is going to have a detailed wiring diagram for it that's going to tell you what terminals are supposed to be for the high voltage, for the low voltage, for the fault, how to wire it up for different power configurations, how to wire it up for different voltages, especially if you're going into if you start going into like a country that has 240 instead of 120, you go into a country that has a different like a 50 hertz instead of 60 hertz. These are things that you just have to pay attention, and they're going to be different for every single device. So these electrical drawings will show the high voltage and how to provide power to things, and the detailed stuff is typically found either in detailed loop drawings, which I'll show you some of, or you'll have to find that information from the manual. As I'm sure the electricians can tell you, drawings typically from engineers, especially if you're getting electrical drawings from civil engineers, you'll always have to look at the manual. So here, what we have is this would be an example of a single line coming into a facility. We've got our incoming feed from a pole mounted hydro transformer. This would be the pole mounted hydro transformer here, 120, 240. So it's implying that it's stepping down the voltage to 120 into here. So 120 and 240, that's the same transformer. 120 is just 1/2 of a 240 volt circuit. It could be stepping it down. It's not listing in this note, but it could be stepping it down from almost anything. 600 volts is typically what you'll find in a lot of manufacturing facilities, or 1440. Oh, go away, Spotify. That's right. Cantico. Grounding. So again, like I said, this is very oversimplified. You typically wouldn't just wire ground right into power here. There's going to be a specific way to ground out this transformer safely. Over here, you've got the hydrometering station, the meter base, just like your house. Every address that receives electricity is metered. This meter would likely be provided by Hydro One or Kitchener Wilmot Hydro, whoever's in the area. We've got here number 3 AWG. So that's a specification of what the wire is. This dashed line here indicates that this is a panel of some sort. This note here indicates it's an electrical cabinet. The power comes down, you can see it goes into LPA, which comes into a 100 amp breaker. You can see, we know that's a breaker from one of my previous slides. There's its rating. It comes down to this little squiggly. I don't know if there's a real term for that, but that indicates that there is a break and we need to go elsewhere to get more information. We need to refer to lighting panel LPA schedule. So one of the things that you probably just noticed is this electrical drawing, it reads in a line. If we follow this, we're following a single line. It's yeah. Let's jump from here over to the lighting. Oh, sorry. Circuit breaker connects to the lighting panel schedule. I should have been clicking while I was talking. I apologize. So wiring diagrams, let's jump over to the lighting panel schedule. So you need to find out what's going on in the lighting panel. Well, here we've got one phase, single phase 240, 120 volt panel. So you've got each one of these phases is 120 coming in. No, it's a single phase. Don't listen to me. Lighting panel A, NEMA 4X. So NEMA 4X is a standard for that panel that will imply the type of seal, a type of environment that you can install this panel in. There's a couple of different levels. NEMA 4X is a pretty rugged one. I believe this is washed down and maybe chemical resistant. I might be wrong. Wash down typically means that somebody can spray it with a hose to clean it off. I think that could be just being NEMA 12 though. Double pole, double throw switch. So you've got two poles, and when you throw the switch, both of them will move at the same time. They are physically linked. Down here, we can see all of these powers, all of these are fed from the same line. What? These are all fed power from the same line, are they? 1, to, no. That is incorrect. That one's connected here. This one's connected. These are not fed from the same line, but they're fed from the same breaker. What? No, I don't think that's right.
Yeah, Ryan,
Yeah?
single phase is considered two lines too, so two hots.
Yeah. Yeah, so this is hot. There's no
Right.
neutral. There's no
Yeah.
neutral being shown here.
Right, so that's considered single phase, two hots.
Yeah, I know. It's there. Each of these is 120. So 240 is the sum of both of them.
Yeah.
But yes. Sorry, what did I mess up? What did I say?
No, I think you're good now.
Yeah, I was rambling and I started saying something else.
Yeah.
But it wasn't it's not switching the neutral up here. Each of these are 120. So
Yeah, right.
each individual line. So each one of these is 120. It's being broken into your 15 amp fuses where these dots are. I don't know why this box is here, because the way I read this drawing is that this line, call this A, L1 and L2. L1 is connected to 1 and 2. L1 is connected to 5 and 6. And L2 is connected to 3 and 4 and 7 and 8. So I read this that this is incorrect. So I would actually, yeah. Or these.
Ryan,
Yes, hello.
those little circles on the dots are your connection points.
Yeah, no. And so that connection point here is for the whole line, is it not?
I mean, I would count that as, I guess, I don't know, it looks weird.
It does. This looks like an odd example.
Yeah.
And this is in the assignment for next week. And this might harken to a note that maybe there's something wrong with that. I don't know. It looks weird to me. I'm going to show you more drawings of lighting panels. Hopefully it'll make more sense. Fuses indicate here you've got your 15 amps going to each one of these devices. You're even showing you've got 15 amps going to spares. Again, fuses are different than circuit breakers, where once this fuse goes, it has to be physically replaced with a new fuse. So here is an example of electrical drawing. So these are going to be powering up the devices inside your panel. So what we have here is these two lines are showing 120 volts coming from lighting panel A. I would like to see a circuit. So circuit 3, maybe, depending on what you saw in the lighting panel. It's always nice for the electrician to know which breaker they need to turn off to turn power off to the panel. We've got 120 volts, typically line coming in here into the circuit breaker. We've got N here for neutral. For 120 volts, you'll have a hot or a line and a neutral. And over here, this is ground. So you could have somewhere on here, it should indicate ground. The power comes into circuit breaker CB101, 15 amps. And you'll notice here, CB101 lines up here with the line numbers. So again, as I was just saying, we've got hot or line, neutral. And these are our line numbers. So If you're familiar with mechanical drawings at all, the left side. So Robert, the left side what? I didn't see that for a bit.
Oh, it was the previous one.
Previous one.
Yeah, but doesn't matter really.
Okay, okay, great. Okay, I'm sorry I missed that. So if you're familiar with architectural or mechanical drawings, you'll see inside a lot of drawing title blocks, you'll actually have like an A, B, C, and 1, 2, 3 grid going up the side and down the side of the drawings. For electrical drawings, what you're typically going to see are line numbers. These will be broken down into, or should be. So again, not every company follows drawing standards, but there should be a correlation between O1 and your drawing number and your line on those pages. So CB 101, if your drawings are, if you set your drawings up properly and you've built your panel properly, in this is my opinion and that of who designed this. If you look at circuit breaker 101, this should indicate, and what we're indicating here is on page 1, line 1, you'll be able to find your information for where that circuit breaker is. Good drawings with well-labeled devices, which correlate to tags on devices and panels, make for better and easier troubleshooting. So here, so we have the device number is dependent on the line number. Oh, so CB101, 0101. Delete these. There were a button to clear those. Okay, so same drawing, just down a few lines. Again, more line numbers. CB 106, 15 amps. Again, dependent on the line number that the device is found on. So this device is on line 101. But if you look, the wire number after it, so we've got 01051 for the wire number here coming into CB 106. Coming out of CB 106, we have 01061. Well, when we come down here to line 9, we still have 01061. But on the other side of CB 109, we have 01091. Now, you might ask yourself, why don't the wire numbers increment up with every line? That's because all of these are electrically the same point. So if this wire comes down to a terminal block here and a terminal block elsewhere, if you were to put your meter on any of the points, your electrical meter, you are now on the same point electrically. The wire numbers increment up when you cross over to another device, when you move into a different panel. That's when you would change the wire up, because like we saw with the single line drawing, when you're coming down, this wire, this 120 volts coming out of this circuit breaker is supplying power to all of these different devices. On here on 0108, there could be a light over on the other side, or there could be a control relay. We wouldn't increment up the wire number until you got to the other side of it. Are there any questions about that? Does that make sense? Does that not make sense to anybody? Okay. So this might have been a lot, but we're gonna conclude, and then I'm gonna open up some drawings. So electrical drawings are comprised of electrical symbols, connections, line numbers, and device numbers. Instruments are typically identified by circles with lines in them or lights with lines in them. Sometimes you'll actually find instruments with special custom designs on them. It all depends on who's drawing them and if they are following any standard. Electrical drawings are simplified drawings, conceptual for wiring the facility to know where the different power is, 600 volt, 120 volt, to get circuits and control circuits. But when you get down to more detailed drawings, more detailed wiring, you need to either look at more detailed loop drawings or the manuals for those particular devices. Any questions? Great. Let us. So we'll start with. So here's a drawing set from a while ago, 2013. So title page. So this is what a typical PLC panel drawing set would look like. Stylistically, they might change a bit from panel shop to panel shop, but you'll have a cover page, something that lists all the different drawings that you have, project number, some sort of title block. And then this is an example of a legend. So the legend will list the different types of devices you would see. This would correlate to something in your P&ID drawings or on your electrical drawings. You've got your contact symbols that are being used throughout the drawing set. When you are drawing these, you will typically use this to copy and paste. Maybe not so much anymore if you've got an electrical package for your CAD, but you've got your e-stops, your start buttons, stop buttons. These are your handoff auto or local auto off remote 3-position switches. Can everybody see these? Should I zoom in more? Okay. Here I'm going to zoom in more anyway. Off to the side here, you'll have different switches. You've got temperature switches, limit switches, level switches, pressure switches, float switches, and then generic switches. And they'll show here, you've got a rise, break on temperature rise, you've got a make on temperature rise, you've got your normally open, your normally closed, and you're normally closed and normally open depending on which direction you're looking to measure your temperature change in, your float change, your pressure change. So if you have a bunch of different types of switches, it might be important for you to make sure you specify which ones you're using for the different processes inside of your drawings. Here we've got control relays, 2-layer control relays, contact points, timing switches. So these would be open and close on timer delays. We've got generic 120 volt devices, fuses, overloads. You can see lots of different examples. Up here, we have instrumentation line types. So depending on what the line is, if it's a bunch of dashes with slashes, Dashes, it could be capillary tubes, electromagnetic, mechanical linkages, DH plus. So this is for your comms. So Ethernet, T1, fiber optics, all of the symbols that are used in the drawing set should be in the legend so that if somebody looks at it, they understand what they're looking at. This is a very basic network drawing. We can see that we have a computer, we have an IP address of the computer, it's plugged into a printer. These are plugged in via unshielded twisted pair, which is Ethernet, to a network switch. It's connected to a Compact Logix controller. That Compact Logix controller has a remote rack. It's connected via a cable. And over RS-232, this processor was plugged into an auto dialer, which was then plugged into a bell line for a dial-up remote alarm system. This would be the layout of the PLC panel. So this is the front of the panel here. It has some displays, some labels. The auto dialer is mounted to the side of it. We have a section view here showing the inside. There's a termination enclosure, some light switches, uninterruptible power supply or a UPS shown in the bottom. Panel layout, preferably to scale. So you got your processor at the top. You've got all your different terminal blocks. TB1, so these are labeled TB1, TB2, TB3, DI1, DI2, DI3. So that would be your power. Probably, I don't remember this panel, but probably 120 volt. And then 120 volt non-UPS, then UPS power. That looks like a 24 volt power supply. These will be your digital input terminals, your digital output relays, and your analog input and then analog output relay. Analog input and analog outputs. So these are all labeled receptacles. At the back of this panel, this drawing set, these terminal blocks, I'm flying to the back on purpose. All of these terminal blocks here are labeled. So TB UPS, and then this should be what the label on the terminal block is, and then the wires and where they're all connected. So this would typically be hopefully something you would get back, should be inside your panel as an as-built. Sometimes you will never see a terminal block layout, or it could be penned in a whole bunch. Again, the more information you have about your panel before you need to troubleshoot it, the better. This would be the power distribution of this particular panel. So at the time, this company, they had a different layout for their wire, their line numbers. So they had, and I know this because RC is me, they had an electrical package for CAD that auto-generated all of their line numbers. So it automatically put them in these funky hexagons. 1, 2, 3, 4, 5, 6. No, not yeah, hexagon, double trapezoid, hexagon, I think. Somebody will correct me. 120 volt coming in, neutral, ground. It says here it's coming from 120 volt, 60 hertz from MCC panel. We don't get to know what breaker it is, but hopefully it's labeled on the other side. They had a main switch here. So a selector switch to turn power onto the panel. Then we come into fuses. So we've got 120 volt coming in, line 1. So all of these terminal points are going to be line 1. So line 1 will come into this side of the fuses. Notice how they're all lined up nicely. This is preferable. So all of your, especially any of your devices that are going to be jumpered together, line them up. It's very pleasing to the eye. Then we see here fuse 1. We have F1 coming out of fuse 1. It goes to the light switch F1A. Then F1A goes up to the light switch, and then neutral. That then creates your electrical path. And that's how you read that first line. There's a 1 amp fuse. We have a 3 amp fuse for a computer receptacle, a 1 amp fuse, clarifier, sand filter, solenoid valves. This particular water plant had some funky air solenoid valves for their sand filter. This is a surge protector. It's labeled surge protector, so that helps. If you're not going to use standardized symbols on your drawings, hopefully you label what you have. Here we have, this says a 16 amp circuit breaker. So that's probably a typo, but maybe not. It's CB1. So here's an example of CB1 does not line up with CB57. So like I said, I worked for this company and this is how they labeled all of their equipment. They went 1, 2, 3, 4. They didn't necessarily line everything up with their line numbers. So here's an example of this doesn't comply with what I said in the lecture, but this is a panel that was installed. So not everybody follows the same thought process on how to label everything. The key here is making sure that your point, you know how to read, how you can identify the size of breakers that you need. 15 amps is a typical breaker. That's what's in your home mostly, are 15 amp breakers, unless you've got your washing machine might be different, your dryer might be different. You might have 2 breakers connected to one another. They're typically 240 volt circuit, but they could be 220 amp breakers. But typically all of your receptacles will be 15 amp typically. And so 15 amp, 16 amp breaker provides power to this UPS receptacle. This UPS plugs into the UPS receptacle, and now everything below this UPS receptacle is UPS protected. That, oh my goodness. These drawing notes don't stick around. The UPS, that means that if there's a power failure on the main line coming in, the UPS is designed to keep everything that's connected to it on for as long as its battery can hold. We've got here indicating that there's a network switch plugged into the UPS, and the auto dialer, the Rayco auto dialer, is also plugged into the UPS. Here, LU, line UPS, we see that we're providing to fuse UPS 1, filtered water color analyzer, filter water free chlorine analyzer. So instead of showing all the connections here, you can see that 1607, these blocks indicate that there could be, we go to 1607. That flow meter provided power by line 516 is coming to this flow meter. So even though they're not labeling all the devices by their line number where they show up first in the drawing, they are using 1607, sorry for flying all over the place, as a location to move to through the drawings. So This one's not showing those squiggly lines. It's giving actual blocks where these wires will leave and go to those devices. This dashed line, if we go back to this drawing sets legend, you can see that field wiring is dashed and internal wiring is solid. So I would take that to mean that all these solid lines are internal to the control panel, and anything dashed is leaving the panel, going out to these devices. So on fuse 3, we've got flow analyzers. On fuse 4, we've got a flow meter. Fuse 5, we got, excuse me, filter wash flow meter. 6, 7. You can see all these fuses again, going out to their devices. And if we move through, we'll find where those instruments are elsewhere in the drawing set. They look like they're all on IO drawings. Again, here, backwash tank level. It's on 1903. So if we fly to page 1903, we have another analog input from a backwash tank level. The instrument itself receives 120 volt power. And then this is the 4 to 20 circuit for its analog signal into the PLC. Sorry, I'm going back more. If there are any questions while I'm doing this, please stop me. So again, more fuses showing we were powering up the different instruments. Here on FU17, we've got the PLC rack 0 power supply, and on fuse 18, that's PLC rack 2 power supply. Those are our 2 compact Logix racks. Each one requires its own power supply. Down here, we have question marks. That's fantastic. Wires that come into these control relays, and then they don't know what they do. I don't remember adding these to the drawing, but this is not the first time I've seen this. Sometimes there are control relays inside the panel that nobody knows what they do. Yeah, that's all I have to say about that. Here we have a float system. So 120 volt from fuse 12 on page 5, line 25 provides power to these terminal blocks. These terminal blocks then leave the panel. So terminal block 1, 2, 3, 4, 5, 6, 7, 8. These terminal blocks leave the panel, go out to level switch low, level switch high, level switch low, and level switch high. When they come back, they will turn on different control relays inside of the panel. You can see here the normally open contacts of those control relays are wired to 4 different locations inside of this panel. So if we go to 622, which is this page, and it's right here, it's wired to literally nothing. Fantastic. We go here, 623 is wired to stop high lift pump. 624 is wired to stop backwash pump. So these floats are wired to positions to stop the HLP, which in this case is a high lift pump, BWP, which I believe is a backwash pump or brake water pump. These would be these high level switches. So these reservoir clear well switches, when they're high, they will force stop the well pumps. So the well pumps can't run if the reservoir is too high based on these level switches. And these well pumps also can't run high when clear well level 2 is too high.
Hey, Ryan.
Hi.
Just a quick question on this
Yep.
drawing.
Yes.
I'm not too familiar with wire tags. I'm just trying to wrap my head around it. I see some locations, the wire itself, they're calling it 2468. How is that determined? Well,
Okay. So
would it be like 601 or 603, 605 like that? Or would it be 2468?
okay, so this drawing set that I pulled from my archives, likely these were backfilled based on the wire tags that were found in the field. In my lecture, I did say that you want to label them based on location or some sort of incrementing fashion that lines up with your page numbers. This particular drawing set, as I'm going through it now, I do vaguely remember this project, and we had to make drawings based on current conditions of the site. So we didn't necessarily have that luxury. Some of these circuits existed before we went in to add the filter panel. So these wires, I suspect, were just put on the wires by the electricians when they pulled them in. What you'll see in the field is electricians will pull a bundle of wires from point A to point B, and they'll label them, and they'll have like a pack of just 1 through 9, a whole like thousands of stickers, and they will just label all of those cables that they're pulling. And if they're not told what to put on them after the fact, so if there were no drawings that said, hey, this is actually going to be 601, 602, 603, they're just going to leave them as 2, 3, 4, 5, 8 because that's the labels that they put on when they pulled them in. So in this case, yeah, you're right. These don't make any sense. And it's highly possible that you would end up duplicating when you label them like this. This particular site was completely hardwired before we added this PLC in. So there were more floats that when the level got too low actually started pumps instead of just interlocking them, and we added a PLC to it to give them some automation. So when you have to do such a big upgrade with existing equipment and existing infrastructure, unfortunately, you don't always have the luxury of being able to make up wire numbers for that equipment.
I
Did
see.
that help? Did that help?
Yes, but say if you have a new equipment going in and you're starting from
Yeah,
scratch, is there
abs-
like a standard or a spec or a thing that needs to
No.
be followed in a drawing for a wire tag?
No, unfortunately. So there's no universal spec for that. That is going to be dependent on the standard and the style of the different companies. So when we go I'm going to jump soon to the standard drawings that my colleague at the city has put together that we hand out to contractors when they want to do work and do drawings for us. And there is a standard to it. I'm just going to show you a whole bunch of drawings today. I randomly picked this one, and I it's not that I regret picking one that is kind of a shit show, but this is going to be, if you end up doing programming and if you end up going in and out of panels that already exist, this is going to be more representative of what you'll likely find. Just kind of a mix mash of whatever is found in the field. Most of the time, everything's in pencil. So I'm really trying to just show you a whole bunch of different drawings, because the more you see, the more you'll know. Does that help? Is this confusing anyone? Is there anything something want to see specifically? Okay, I'm gonna try to run through this one faster and then switch over. So you can see here on this page, it's actually, we have a 24-volt power supply. So it's receiving 120 volts, and then out of it is coming 24 volts DC, similar to a transformer where you've got one type of power coming in and a different one leaving. But switching from AC to DC is a different process electrically. But everything here is now 24 volts DC. Electrical theory is the same. Voltage equals current times resistance. Did I get that right? PIR, yeah, PIR. Yeah. I am blanking on that equation. I'm sorry. That equation. Voltage equals current times resistance. So that's the same for DC as it is AC. So when you're looking at this and you have a device that has a specific power rating, voltage, you can calculate its required protection the exact same way. What's important when you look at these is if you see devices, if you saw a 50 amp fuse here for a PLC input card, that's a problem, because if something were to happen, if you were to have a short and 50 amps after actually came into it, there's no way that it would be able to survive that. Not only might you destroy your PLC card, but you could destroy your 24-volt power supply because its circuitry can't output that. Probably limited somewhere, you might not blow it up, but you might lose all your 24 volts on this side. If you lose your 24 volts on this panel, well, you lose all your cards because all of your cards are DC modules. So when you're reviewing drawings, it's important, especially if you're doing it as the designer, as the constructor, if you're specifying and you're putting in equipment, you want to make sure that you're putting in adequate protection for it. But you also need to make sure that this power supply is large enough, has the proper output using the power calculations to provide power to all the devices downstream of it. You can see here all the different fuses, FD1. So again, we had F1, FU1 for the UPS, and FD1 here for the DC devices. And then we've got our output modules, some pressure transmitters, level transmitters, and the DO cards. Moving on from power, you can see now we're getting into the IO wiring for this site. So we have a DC input card. This is an Allen Bradley 1769 IQ16. So if you were to look that up, that's a Compact Logix IO module, a DC 16-point syncing input card. You can see the second module is the same card. What we have here are IO points and how they're electrically wired up. So we can see here I:00 connected to a terminal block 1. That looks like a typo. This is probably labeled I0100 in the field, not TB1, but I'm not in front of the panel, so I don't know. We have a spare input, a handoff auto switch, another spare input, handoff auto switches. It would be important if you were reviewing these drawings, it would be very important to make sure that these might line up with any IO lists that you have. If you have the PLC program or you're going to be programming the PLC program, making sure that your program lines up with the IO that's going to be wired. IO wiring diagrams like this that are sent to electricians or sent to panel builders. If it's sent out and it's incorrect, there's a good chance that it'll get wired incorrectly, which will cost you time. It might not get wired properly. Some electrical contractors, they will ask questions to get it rectified. Other ones, they don't. I don't want to say that electricians don't know how to wire PLCs, but there are electrical contractors who do a lot of industrial work, who do a lot of high voltage. They're good at doing lighting, MCCs. If they do a lot of residential stuff and then they're thrown into a control panel, maybe they don't know what they don't know, and they could wire things wrong if the drawings aren't correct. I've seen it, I've lived through it. I've seen some electricians let the mysterious smoke out of equipment. I've let the smoke out of equipment by not paying attention. So it's important to make sure you get voltages right. You can see here, there's dashed lines that indicate different locations where wires are going. This is a style thing. Not every panel builder will do it, but this one is indicating that these IO points here are being run to the genset being a diesel generator for the facility. These ones are going to a backwash panel. So these were those floats that we saw earlier on one of the other drawings. Valve chamber, we've got some more floats and some more contact valve statuses here. Over here, we've got clear well, low level alarms. So these are going to be coming from floats. I don't love the way these jog back and forth, but it looks like it was done so that the descriptions didn't overlap one another. When you can't be pretty, be legible. Here, it looks like there's actually wire numbers with letters. This is a hot mess. Again, more IO. This is a DI card. You can notice here, here's another standard for how IO is wired. So when you have, this would actually be run this way. So if you have a panel with 3 IO points in it, you could either run, the electrician could either run 6 wires out to it and run 2 back for each input, or you can run 4 out, 1 which would be common up to each one of the inputs, because electrically this is the same point, and then 1 back for each. So this is a good example that sometimes, even though you have 3 inputs, they might not have wires individually for each one. So it's good to see that. Does everybody understand what I said there? Perfect. So these are digital inputs. These are analog outputs. So analog outputs for this facility look like polymer pump speed set points. So telling pumps how fast to run. 2 polymer pumps, 2 ammonia sulfate pumps. Then we've got digital outputs. This particular panel uses what are called interposing relays. So we have a 1769 OW16 that is wired up to control relays, 24 volt, you can see here, 24 volt control relays, and then the contacts of those relays. You can see here that the normally open contact of RO1 is well pump number 1. It just says well pump number 1. I'm assuming that's run command. Run command here. So the normally open contact of this control relay, well pump number 2 run command, coagulant run command, potassium permanganate, high lifts, backwash pumps, scour blower run command, NaOCl pump, sodium. Sodium hypochloride. Interesting. Backwash valves. And so this is what you'll see for output cards. And you'll notice stylistically, most of the time you can identify them without even needing to look at the cards, where input cards typically are read left to right, device into card. Output cards are card out to device. They are delineating here where the field is and where the panel ends. Here again, we've got output card to device. These contacts exist inside the control panel, but these devices exist in the field. Here we have another output card, but it looks like they're using different voltages for different outputs, which is why they're using these interposing relays so they can switch voltages up individually. So you can have 120 volt wire, you can have 120 volt power for some devices and a different 120 volt for other devices. Does that make sense? You can see here where this 120 volt from 505 comes down. These wires jump over it. This is another way of indicating that wires aren't connected. And then it passes down. It is connected to these devices, but none of these ones. Everyone see that? Where these 120 volt comes up here, neutral will complete the circuits. Might look confusing, probably looks confusing. Again, it's one of those things you've got to see a bunch of times to be able to pick up quickly. Again, field devices for the clarifiers inside the panel. Inside the panel, we have more field devices. It looks like these ones, again, are supplied power. These ones are only using the contacts. These polymer pumps must send and receive that power themselves, so they must have power supply internally for their run commands. And we've got analog input devices. So again, field devices move to terminal blocks, move into the card. So we've got a pressure loop. This is a distribution pressure, PIT, PIT01, or it's being called IT 1503. So that's lining up. This is the first thing, one of the first things I've seen that's actually lined up with the wire numbers. So this device is loop powered. You can tell that here, this 24 volt power supply is put into the 4 to 20 milliamp loop. It provides power out to the device, comes back into the card, and it will return down to 0 VDC somewhere. It doesn't look like they've, then it returns down the 0 VDC here. This level looks like it's receiving power from 526 on fuse 13. It provides power to the panel meters. These are 4 to 20 milliamp water levels. Backwash flow. This instrument's provided power by FU5. So I'm gonna switch to a different drawing set. I think you guys have got this, unless you have questions about this drawing set. I'm gonna switch to a different one. Okay. So another client, this is a sewage treatment plant. Here's their legend for this drawing set, showing the different terminal blocks they're using, the coil contact examples, the coil examples, latching coils, your push buttons and switches, different temperature elements, input outputs, and then different electrical drawings, electrical circuits. This drawing set is more encompassing than just a control panel. This is another thing that you'll see a lot. Sometimes the control drawings are embedded in larger drawing sets. This is the single line drawing for the upgrade at the Hagersville Water Pollution Control Plant. Single line drawing is the main power coming in and how it gets distributed out to the different buildings. So you can see here, we've got a 27.6 kV 3-phase transformer comes in from the pole. There's a lightning arrestor, which is protection from lightning. And there's a load break switch on it. If you've ever seen one of these, if you've ever seen a giant, it looks like a throw switch from some evil villain's lair mounted to the side of a panel, electrical pole. That's what these throw switches are. Here's another example of how you could find a transformer. So this is, instead of those funny loops, this is showing another 27.6 to 600 volt and to 347 volt pad mount transformer, 1500 kVA. So pad mount transformer versus pole mount transformer versus wall mount transformer. It's showing, I believe this is delta Y. And then it's listing the conductors 6 times 4C, 750 MCM plus grounds. So this would be used for the electrician, the general contractor, or the electrical contractor to know how many and what power feeds to pull from the transformer into the main building. This is a 1200 AT main breaker. This big one, utility meter. This is an ATS, so an automatic transfer switch for the facility. This transfer switch is connected to 1,000 kilowatt diesel generator. So when normal hydro's on, you'll have power come into the plant. When power fails from hydro, this generator will turn on, come into the ATS. The ATS, this contact will actually switch over and then provide power. There are dozens of connections inside of the ATS, but on this drawing, we don't care. We just need to know that there's an ATS, there's some transfer information, and the additional wiring for that, for faulting, for tripping, for what position it's in, that would be found elsewhere. Comes into here, this would be a power monitor. These are going to indicate some sort of CT or PT, so current transformer, potential transformer, to read power information coming into it. And it says Ethernet, so it's monitored by some computer somewhere. Here we can see the main bus of the plant. So everything inside this MCC is 600 volts, 1600 amps on the main bus. So there's 1600 amps to use spread out across all of the different breakers. MCC stands for Motor Control Center. It would physically, this is a layout of what the front of it would look like. So here we see hydro metering, so and main breaker. So these wires pulled from that main transformer will physically come up through the floor here into this main breaker. Inside this giant metal box, that's where this main breaker is going to be. It's a circuit breaker, but it's much, much bigger. If you can imagine, if you've ever seen the original Jurassic Park with Samuel Jackson, when he's like in that tunnel and he's like priming that handle to like turn the fence back on, that's what he's pumping. He's pumping a main switch like that. Not like a normal circuit breaker. This thing is high voltage. High voltage, well, high voltage, high amperage. These different MCC buckets, sometimes they're called, or sections, they will have, there's actual physical bus bar running behind these that these will pull their power from. Each one of these sections that we can see here will have a breaker associated with it. So, and some of these lines will run from one building to another. So these single line drawings are this power distribution drawing for, this one's called, they're calling this one a single line drawing. We'll show you've got 60 amps going to a SPD. SPD is that, it's a surge protection device. We have 600 amp 3-phase, whoops, going to the inlet works building. This one's going to the filter building. We have a 20 amp breaker, number 310 plus a ground running to a 15 kVA 600 to 120 208 transformer. So there's another transformer that's going to step down from 600 volts to 120 volts. That's going to supply power to lighting panel A. 600 or 400 amp here is going to connect to a contactor. It's going to connect to a power factor correction capacitor bank. So you can see here that capacitor symbol that I was showing you before. These, if you get into more electrical theory, you'll have leading and lagging, and you'll have a power factor of a device. Well, when you get to a certain size, you'll actually have a power factor of an entire facility. This power monitor will monitor the power factor of the facility, and it will turn on and off different capacitors to adjust it. And at 600 or 1600 amps or higher, where were we at? Yeah, 1600. It can make a huge difference in efficiency, because I believe this plant had like 150 motors running sometimes. What we got here? 150 amps to run to a blower. That's really just a big fan that blows bubbles in a tank 5 times the size of a Olympic swimming pool. And they got a bunch of those. So this is for different valves for diverting air. 15 amps, 3-phase each. The motorized gate for the facility. Area lighting. So we've got a lighting. There's probably a transformer in here for the lighting with an overload, or maybe just a contactor. I'm not sure what that is, but there would definitely be additional drawings for that. And we've got some VFDs for different sludge pumps, more valves, and some spare breakers. Any questions about this single line drawing? How to read this single line drawing? Am I going too slow? Am I going too fast? This is a single line drawing continued. So from MCC1, this actually goes out to MCC4, which is in the filter building. So you can see again the layout of the MCC. So the motor control center further out in the facility. It has breakers that go out to all of its different devices. UV system. So the UV system hits water in the wastewater plant, kills bacteria in it. We've got a bunch of filter gates, fans for exhaust systems. So anything electrical, any large electrical thing is going to typically show up on a single line drawing. You'll see single line drawings for larger manufacturing facilities. Here's more single line drawings. We're getting close to 8, so I want to get through as many drawings as I can. This is really all I'm going through drawings for the rest of the class. So if you guys want to drop off, go for it. I'm just going to be talking about drawings. MCC1, again, you've got more. This looks like it's an old metering cabinet. This particular upgrade that we did, they did decommission part of it. So you can see here, these dashed lines mean that equipment's being removed. So the original meter, the original MCC was being removed. What about the group assignment? Yeah, so that will be assigned next week. There is nothing due this week. Yeah, thanks, Vincent. If you can't make next week's class, let me know. I need to break all you guys. I need to break everyone here up into kind of even distributed groups based on who's going to be here. If you can't, let me know. I know there's 2 people who cannot, so I will make arrangements with them. Yeah, it'll be a group. So just there'll be a group assignment. There's going to be drawings. Will there be? I will be. Just want to know if there. No. I'll assign the groups somewhere midweek. My plan is to kind of post what it is. You guys can take a look at some of the drawings. You're going to have a drawing set. I talked about it in the lecture. There's a drawing set, and then next week, the first lecture before you guys are let loose, we're going to go over what shop drawings are. I'm going to show you a couple of shop drawings. Then you're going to have drawing sets to review, mark up, find issues with them, compare them to your shop drawings that you're given, and then send that back in. If you want, I might be able to get through the lecture for next week too. I haven't really read through it, or if you want me to keep going through these drawings, if I get through the lecture, I could post that assignment and then assign groups this weekend. Let me know if you guys have a preference, or would you rather wait until next week and just not have to worry about anything this weekend? It wouldn't be due till the following week anyway. More MCC layouts. This is where we get into more field devices. So this is an engineer's. So this is a civil engineer who's made a field control panel typical drawing for a VFD. So I don't know if we've touched on VFDs. I was kind of chatting with one of you guys who was asking about VFDs. And VFDs stand for variable frequency drives. They are used to connect to motors to run them at different speeds. So when we were talking earlier about a Hertz meter, Hertz would just measure the frequency in cycles per second of a device. So you'll have, if you need to run a device or a pump at a specific RPM, you could scale this pump to run at a specific frequency, and you would have to do some math to match the frequency with its speed based on the pump rating. So that was a mouthful. If anybody has a question about that, I can repeat it. So you can see here, you've got, so this is where you're going to you get a 600 volts. So this would happen inside the MCC. This would not be in a PLC control panel, but it's important as a controls programmer to know what's going on inside these MCC buckets. So this VFD would actually live, I say live like it's alive, but inside one of these. So let's say it's a ROS pump. So return activated sludge pump, VFD, and reactor. So inside each one of these sections is going to be this. So this is a typical VFD drawing that this engineer has put out that outlines the function that they want to get out of the drives, but may or may not actually have the wiring exactly based on the equipment being supplied. So this is a large engineering tender drawing set that has been sent out, that has been designed to do a specific task, but not necessarily done to the level of detail where you could wire based on it. If anybody doesn't understand what I just said, let me know. But that is how the municipal environment works. Even some manufacturing facilities, they'll do that. They'll hire an engineer to design something, to do a specific thing, but they might not get it at 100% in the design phase, and they'll put that out to bid. So people will bid on it and then fill in the gaps later with shop drawings. So here you have a VFD that runs off of 600 volts. There's a 600 volt to 120 volt transformer. This would be inside that electrical panel. It will step down the 600 volt voltage to the control of this VFD, so this pump. So the pump, then the motor for the pump is connected to the VFD. So you have 600 volts coming in, and then you have the control voltage going out that will be that could be varied to run this pump anywhere from technically 1 hertz all the way up to 60 hertz. But based on the motor itself, you might not be able to run it less than 50% of its maximum speed, or 30 hertz. So here inside the circuit, this is where you're going to see a lot of your symbols. You've got 120 volt coming off of the secondary side of this transformer through a main fuse. There's grounding here, and this is going to be your neutral for your transformer. It comes down, we can see that it branches, it comes to this red light. This red light indicates that power's on. This red light also indicates that power's on. Why there's 2 lights? Hard to tell. This one is the local control station. I'm not sure where that light lives right now. There could be a remote button station. Yeah, so there's a remote button station that's probably lives next to the pump. So yeah, I'm trying to remember the site. These pumps were in the basement of this building, and the MCC was on the top floor. So that if there was a flood in the basement, you didn't flood out your high voltage. So these local control stations, they were downstairs right beside the pump. So if you needed to put the pump into local off or computer based on this drawing, or handoff auto, you could do that down at the pump. Yeah, without having to go up and down the stairs a bunch of times. So power comes down, comes into this local off computer. One of the things, this is a good one. This is a good one. This is probably the main reason I picked these drawings. You can see here, you've got a local off computer. This is a 3-position selector switch. There's no, if there was an indication, if this were broken, if you had a selector switch that did something like this, it could indicate that maybe, let me undo that for a second, because there would never be one like that. So if there were some sort of spring, a switch that looks something like this would indicate that it could be 2-position with a 3rd position. Because that's broken, it may spring back to the center. So it could be a hold position, but this one's only momentary. You can see that for 2 position selector switches as well. But here, because it's 3 position and there's no break in any of these, it will hold any one position. These X's and O's, they are meant to indicate which position is true. So when this switch is in local, this path, so because this is local off remote, local off computer, when this is in local, this is true. When it is in computer, this one's true. When it's in computer, this one's true. And when it's in local, this one's true. So when you see these type of linked, again, this is linked just like that other switch we saw in the lighting panel. This is physically linked. So this is all the same button. And when this switch changes, when it's in local, these push buttons start, stop, FF. I'm not sure what that is, a fault of some sort. This is the starting circuit for the pump. So you can start it. It'll close in SS, which is the start here. When SS closes, it looks like that's the indication that this drive is going to run the pump. Here we have an AI, so there's going to be an analog input from the PLC to indicate how fast the pump is going, and the speed set point is an AO. So this is indicating that there's an analog output from the PLC that's going to set the speed of this pump, and an input that's going to read the pump back. Down here, again, when it's in local, again, down here we have CR2. So when this is true, CR2, that coil will pull in, and this is hand mode. So again, this is an indication here that this is going to be wired to a PLC. So if we were to go back to the legend and find this circle with an X, we'd probably find that that is an indication of a IO point of some sort. When this switch is in computer or remote, we can then see that the CR3 will start the pump. So CR3, when we find down here, that's connected to the DO start, and CR4 is a DO stop command. So for this system, it looks like the pump has a pulse to start and a pulse to stop output. So there's 2 outputs wired back to the PLC. Ready FF, it looks like there's a ready command. So this is coming from the drive. So FF looks like it's a signal from the drive. So if the drive's not ready to run, the drive won't run. Once whatever fault that is clear, or whatever state that is allows it to run, then it will run in local or remote. This is the running indication back to the PLC, and this is the fault indication back to the PLC. So this is a pretty good example of a generic, typical you'll find in an engineering drawing set. Sometimes this is the best you get even for as-built drawing sets as to how things would be wired. Note, there are no wire numbers on this. There's a conceptual layout of how things will work, but you are so devoid of information from this drive because this doesn't even know what make and model of drive you have yet, because that hasn't even been specified. All they're doing is, this is for tender, this is a conceptual, we need a pump with a variable speed drive that has local control and VF and PLC control. So this is as detailed as some engineers will get for control systems. These are examples of 600-volt motor circuits without VFDs. So we've got 600 volts run across to the motors. We've got 600 volt to 120 volt step down transformers. We've got local control stations for those pumps. We can see here, we've got the same 120 coming into a CR1, which is not available. So it looks like they're going to use somewhere in the not available, normally closed contact. So when you see CR1, what I'm looking for elsewhere in the drawing is a contact with CR1. CR1 here, there, that looks like the only CR1. So that looks like it's a signal potentially for a PLC. Doesn't show that it's a DI like the other ones. We've got a local off remote switch, where in local, the start and stop push buttons will run the system. The start and stop push buttons, they turn on M. M looks like it seals itself in around the start button. In remote, CR2 and CR3 look like they work. CR2 will turn on M, which will seal itself in. And then CR3 will stop the pump. We've got a light for run indication. EMT elapsed time meter. That's the run time of the pump. Here's an overload contact. Overload contact. Those will physically be attached to the pump starter, and they will trip when there's a fault condition. Motor current overload. Maybe there'll be a temperature sensor, something else wired to it. Over here, we've got a red and a yellow light. So these are lightly, there's a fault light. Red is a running light and fault is a fault light. So when looking at drawings, it's always good to look all the way across. You might have descriptions somewhere that may not make sense until you follow it to the other side. Any questions? Am I going too fast? Oh, here's a layout, a typical starter control schematic that shows power on, running, and a fault light. So even though here is showing multiple, this fault light, because it's in this box, exists on the local control station. And this one exists on the panel front here. Am I going too fast? Am I confusing people? So this other circuit is similar, but it does look like it has integrated timers. So what is that timer? There's the timer. So it looks like when the system turns on, there's a temperature. Yeah, high temperature. So there's a thermometer here. So this is probably a fan controller, blower controller. There we go. Blower schematic. When the temperature reaches a certain setting, TR1 will activate. TR1's a timer. However long the timer is set for, sometimes you will find here, here's the timer. It's going to wait to close on the end of the timer. Sometimes there will be like a 5S to indicate how long the timer is. That's a 5S, not a 55. So this could be set for 5 seconds or 5 minutes, or likely from an engineering drawing set, it will say something along the lines of timer settings to be set on site. What do we have here? Makeup air unit. So this is part of an HVAC system. We've got, what do we have here? Power coming in. We've got a 3-throw switch. So this breaker or switch will open up all 3 phases into the makeup air unit. We've got different switches here This looks especially vague, and it makes sense because here it says part of MAU1 package. So likely this information is copy and pasted from the supplier of the makeup air unit. There may have been a contract for this one, so they just copy and pasted their schematic, and they don't have the terminals for this drawing set. Hopefully they'd be rolled into some sort of site package for that set. More circuits. So again, I know a couple of weeks ago, I kept saying you'll see lots of motor starter circuits. I think you might already be getting the picture that 90% of drawing review is motor starter circuits, at least for my industry. But even if it's not a motor starter circuit, it's contacts, it's relays, overloads. Here's some more supply fan, EUH, which is an exhaust fan. This filter building has a fire panel. It receives here 120 volts from lighting panel 4-21. So you're 24. So you're actually seeing they're already assigning circuits for it. So under a lighting panel 4A, circuit 24 will be for the fire panel. Makes sense because fire panels are normally something that need to be designed because of building code. We've got your different contacts, which will run up to the test button. These contacts will be smoke detectors scattered throughout the building. And these are the fire contacts for PLC, maybe an alarm beacon, MAU, fire contact. So the makeup air unit will turn on. Hopefully you're getting the idea that these drawings, it's hard to look at just 5 drawings and say, now you know drawings, because depending on what it is your project is, you could have a 300-page drawing set, or you could have a 5-page drawing set. And it's impossible for me to get every industry. So I'm going to try to cover a lot of the typical stuff that you could see. Lighting panel layouts. So here we see lighting panel layout. So there's a neutral. What do we got here? So there's a main breaker at the top. And circuit 1 and 2 are connected on the first leg. 3 and 4, 5 and 6, 7, 8, 9 and 10. And you can see how we have 1, 2, 3, 1, 2, 3, 1, 2, 3. This is done to balance out the phases. So each one of these will take from phase 1, phase 2, phase 3, by a 3-phase building, because we know that there's 120 volts coming in and it's broken into different phases. Blower lighting panel. So these lighting panels are scattered all throughout the plant in different buildings. Here's a schematic for photo cell for outdoor lighting. Yeah, and another one for the UV building. D means outdoor lighting, down lighting. So that's a light that points to the ground. It's pretty straightforward. So like I was saying before, these electrical drawings are interspersed with facility drawings. So here's an overview of the entire plant. So now this is what is that? This is general building. So this is a existing generator room. So these are going to be for demolition, FE. These are showing where new instrumentation is being installed. So we got LIT. So you're going to have instruments are being installed in these different channels, flow meters, MG, I don't remember what MG is. I think it might have been in mass airflow meter based on fluid flow meter. This is showing more instrumentation where they're being installed. So we've got HST RAP1 AT, so that's probably a dissolved solids analyzer. RAP, so return activated pump flow, return activated pump 2 flow. So these are overlaid on the electrical, not the electrical, like the mechanical layout of the building. So like I was saying, this is the return sludge pump house. This was that MCC upstairs, and this is the basement where the pumps are located that we were looking at earlier. So not only do you need to know how to read for, at least for water and wastewater when you're doing contracting, you need to understand where is the equipment going to be installed. Is it going to be installed in the basement? If it's in the basement, like, is it water rated? Is it going to be installed in a room where there's, if it's going to be installed near raw sewage, it has to be explosion proof. If you're specifying that type of equipment, and you could very well be, if you're the one who's designing and deploying the software, the control scheme, you're being paid to deliver an automation system, and you have to spec all the parts, you need to kind of be cognizant of where those parts are going to be. And then if you're reviewing these drawings, if you work for an engineering firm and see where some of these things are trying to be installed, well, you might need to pick up that you don't want to install, this is a heater. Well, you wouldn't necessarily want to install the thermometer right across from it. And you can actually see here that EUH02 is pointed right at the thermometer or the thermostat for EUH02. You probably don't want your heater pointed right at your thermometer. You might want to move that. That's a very small thing, but it's definitely something that after years of, oh fuck, we got to move, sorry, I didn't mean to swear, but we got to move this thermostat. That's a day's labor months after the fact, because the room never heats up because it just blows on the darn thermostat and turns the heater off in a minute. So little things. Jib crane. This is that UV channel that I was talking about. Very briefly, here's a traveling bridge. There's literally a PLC panel on this bridge, and this bridge will move down into different sections of this filter, and there's pumps that will stir up the sand at the bottom of these filters, pump it out into these channels into this wet well, but also allow it to filter down and out the side, and then it'll run through these channels that have UV lights in them. I think somebody once told me they're 150 times more powerful than the UV lights you would get in a tanning booth. And there's probably 50 in each one of these. So there's 1, 2, 3, 4, 5, 6. 50 in each one of these channels. So 100 UV bulbs. That just, if you were to look at it without the shroud and all the water in between, it will damage your eyes worse than looking at welding. So an interesting health and safety hazard, and a ton of power running through those. What else? Over here, you've got gas analyzers. So AIT kind of becomes a catch-all sometimes of some sort of analyzer. So this is an H2S, carbon monoxide. LEL is a lower explosive limit in O2. So that's a very standard gas monitoring system. You'll see those in mining. You'll see those in oil and gas. You might actually add a couple of extra things for oil and gas. Very common for water, wastewater, anywhere where you're going to find lots of potential buildup of gases. or the lack of oxygen. That's another important one. Okay, what else do we have here? These are showing tanks. You've got layout for a tank. You've got a motorized valve at the bottom. You've got some float switches for the tanks, some level transmitters. You've got more float switches, a flow meter over here. This is where a truck will drop off liquid into the wastewater plant. That's the last drawing. PNIDs. So I know, I think it was Olu had said PNIDs. So process and instrumentation drawings are a little bit of a different beast when it comes to how they're looked at. They're more process related than electrical related. So if you find yourself in oil and gas, very specifically pharmaceutical, food and beverage, you'll find a lot of drawings like this. Again, they're going to have a layout, sorry, not a layout, a legend to kind of indicate what the different lines mean. I'll show you the ones for this drawing. Oh, this drawing set might not be good. Everything that's kind of illegible was removed from this drawing set. So, that's a shame. I'll try here. So you can see this will show from secondary clarifiers. This is a tag to a different drawing location. And this new flow path will come into all of the different motorized gates. So there's a motorized gate that's feeding HST WWP2. So it's a wash water pump for the filter building. Actually, those are the bridges, I believe. Yeah. So these are those bridges I was talking about that have PLC cabinets on them. And then inside the bottom of the bridge, there's a bunch of pumps and jet pumps that'll stir things up and they'll move up and down. They're kind of neat, a little nauseating to sit on though, when they're moving all the time. Whoops. Whoops, there we go. So you can see here when you have, oh my goodness, I'm scrolling too much. It's gonna let my computer catch up. So you can see here with the PNIDs, because you have an LSH, an LSL, an LIT, and an LE is a level element. So the level element goes into the level indicating transmitter. Here that they're showing a tag for the device. So HST, for this client, it was Hagersville sewage treatment filter 1, and this is LT1. So that's filter 1 level. This is the filter 1 level switch low and the filter 1 level switch high. It's actually level switch high is LS1, level switch low is LS2. And down here we have a filter bridge 2. So we have FLT2 LIT1. So hearkening back to the tagging that we were talking about, I think a couple weeks ago, this is an example of a client who has a standard that you've got a filter 1 and you've got specific tags for that, and a filter 2 and specific tags for that. So the level transmitter is always going to, if you had a third bridge, you'd have a filter 3 and then a level transmitter for that. Well, you follow these up. So how the PNIDs are wired or drawn is you follow those up into the panel, and you can see here, these are the different IO points. So you have a filter bridge, these are clearly scanned. Filter control panel in auto, and there's the PLC tag. Carriage drive running forward, there's the PLC tag. Carriage drive running reverse, carriage drive failure, filter backwash pump running, so on and so forth. So how the PNIDs are laid out is process. So these will help you understand how you would need to program something and detail where all your IO would go. So if you don't have IO drawings, or let's say you were given these drawings, but not panel drawings, you could start to build an IO list knowing, okay, well, I have a filter gate and this is the IO for that filter gate. And I have an existing PLC and I need to add that IO to that PLC. Well, this could help you build your required IO points. If you know how many IO points you need to add, then you can start looking at specifying cards. You can start looking at making guesses as to how long it's going to take you to develop new code. Well, I need to add 10 new pumps. Well, I think each one of these pumps will probably take me a day, so 10 days of labor. So starting using PNIDs is a great tool if you have them to be able to start getting IO counts and building your the idea of your program and getting into pricing and part specking that way. Here we have a filter holding tank. It looks like it's got 2 pumps inside of it. So HST, wastewater pump 3 and wastewater pump 4. We've got some valves, some more switches, so level switches and a level transmitter. It comes up, it's coming into a filter wastewater pump control panel. There's a tag and name for that control panel. And then here's all the IO list, IO that's inside that panel. So it's called a pump 1 remote, pump 2 fault, so on and so forth. I can supply these drawings to you guys if that is something you guys would like. Yeah, these were all removals, so this is impossible to see. Here's a layout drawing for the network. Pretty high level stuff. We've got PLCs in different sections of the plant. Some of them are Slick 505s, the other ones are compact logics. This is breaking down. I'm going to show you better examples of these, but when I was talking about loop drawings, so when you move from an electrical drawing that says, hey, you need to run power to this device and pull a 4 to 20 signal out of this device, this type of loop drawing would specify how you're supposed to do that wiring. Maybe not tell you every terminal on every single device, but this is a level transmitter here. The level transmitter receives power, so line, neutral, ground to these sections of the level transmitter, and the 4 to 20 comes back this way. This would be a 4-wire analog device. This would be a 2-wire analog device because it's only has 2 wires coming back, and it's actually requiring loop power to be provided through it. Another generic, this is a generic analyzer example. More generic examples, so you'll find these all over the place. This is used by engineers a lot, especially with blank labeling, so that the electrical contractor at least has something they have to follow, so they don't wire it the cheapest way possible, or the least expensive, which typically everyone tries to do. If you can do something by pulling 5% less wire, that's 5% less copper, and copper is very expensive. This is detailing electrical connections between the blower panels. There's so much stuff in these drawings, guys. I'm sorry if you're dying here. This panel has some typical layouts for electrical panels, typical layouts for electrical power wiring. I do remember these, and they were absolutely garbage. They weren't scaled at all. The actual panels for these were much, much larger, and those I'm not allowed to send. So some generic loops here. So electrical starter, instrument, current loops. So this is an example of what we have going on at the city of Guelph. Is this normal? some municipalities have this, some municipalities have nothing. But let's say we needed to wire in a new ProMag 400. We would hand this to our electrician and say, this is the contractor, whether it's our union electrician, whether it's whoever, this is how we wire them. This is the PLC we're going to go at. We would give them information as to what IO they're going to land these on. If we had circuit breaker information, we would give that to them, but we would print this out. We would scratch off the information that's going to be valid for that. They would fill in their circuit breaker information. They would redline it and say, this is how I installed it. Then we would go through, we would make the update for it, and we would name it new distribution flow meter for site 5. And then that, because we're a water municipality, we would then have to put that into our asset management system. So if you work for, again, pharmaceutical, oil and gas, water, not so much wastewater, but municipality, you can run into asset management systems that are fairly rigid. They might have lots of drawings, or they might be trying to accumulate lots of drawings. If anybody is familiar with Walkerton and all the clean water regulations that have come from that, asset management is one of them that's fallen out of that tree. Weather stations. Again, it doesn't look like much, but there's your photo sensor and the additional weather station information wired into an analog input. We hand it out to a contractor. They get to see it. They know how we want that specific unit installed. Current, that was generic. Here's one of our pressure transmitters that gets installed. It even talks about ordering the one with the M12 plug at right angles. So it fits on our facility. It fits in all the tapped holes that are already in all the pipes. If we hand something to the millwright to put in and it's got the wrong thread, they'll throw it out. We'll have to order new ones. So sometimes it really behooves you to pay attention to what it is you have. If you're taking one instrument out and putting something else in the new hole, make sure whatever you're putting in that hole is going to fit. Make sure it's the right thread. That's not necessarily programming, that's just in general. And then knowing the wiring for it. Again, here is something that you wouldn't necessarily see in the engineering drawing, but when you know that you're going to use a Wicca PSD 30Q PG 420 and you have 29 of them, well, you have the time and you can exert the energy to make a drawing that will detail the wiring harness that comes out of it and know which ones you want to use in your control schematic. So if you buy this unit with its built-in wiring harness, you get a brown, white, gray, black, blue, and now we know exactly what we need to do with those. So this is what I mean about you don't get all of the information in some of your electrical drawings. You might have to dig around to find this. This is abnormal, at least up until 5 years ago, it was abnormal to find clients who had this type of information. But with the advent of digitized asset management, it's becoming easier to keep drawings in place, even keep copies. That I've gone to some old locations and there's just no way you're gonna find drawings. I found drawings that have been eaten by rats or mice. I don't know the difference once they've eaten paper. Let's look at our Ben Shaw drives. So here's One of the VFDs that we use is from a company called Benshaw. We've picked Benshaw. They're not the biggest name brand, but they're from Listowel. All these drives are made in-house in Listowel, or at least their soft starters are, their drives are assembled in Listowel. So when we need to install a new drive and we're installing one of these ones, this is what we give our contractors, and you'll see 600 volt coming in across the top, line 1, line 2, line 3. We would fill in the amperage we would need it based on the horsepower of the drive, because the bigger the drive, the more the current. These are our current transformers for measuring power. This is the control board, and where we had the generic wiring schematic for your engineering drawing that I showed you. This one, we've gone through the time. This is the control board, and these are all the points that you're going to find on it. We step down from 120. We come in. This is actually inside the panel that comes from Benshaw. So we have X1 and X2 that's coming off of the transformer. We've got our neutral contacts, our live contacts on the boards. We've got our power status. Down here, there's the M2 that'll run the pump. That's the bypass contactor. No, I shouldn't just say M2 will run the pump without digging through the drawing. We have relay 1, relay 2 for running status. They come down here for our PLC. We've got 14 gauge AWG. Again, 14 gauge is the amount of copper in the wire. AWG is stranded wire. I forget what AWG stands for. Our run command from the PLC to the pump goes on yellow wire. Our pump starter power status, which is an input, is red wire. Running status, fault, and remote mode. Remote mode is the handoff auto switch here. In hand, we are not in remote. In auto, we are in remote. We've got our start input, DI here for the device. You can see there's our start input that come up and start the drive. And then our analog inputs are where? Analog inputs are here. Analog inputs and analog outputs for our drive. So this was taken out of the detailed control manual from Benshaw. Here's M2. Power factor correction capacitor for motors that are 50 horsepower or larger. So obviously this M2 is external to the drive and possibly optional. Yeah, we're getting near 9 o'clock. I'll keep going if people want me to keep going. What was this one? All right, so here's a new facility, an upgrade underway that I'm currently working on. So here's a process flow diagram. So it's like a PNID, but wouldn't have the IO in it. Actually, there are IO drawings and our PNID drawings, but we can see from zone 1 and zone 2. So that's just different areas of the city, moves into the plant. 400 here indicates the size of the pipe. So this isn't wire now, this is actually process for water. So we've got 400 mil pipe into a manual valve, into this is going to be a chlorine analyzer, a temperature probe, and pressure. It branches off into a flow meter to fill reservoirs. We've got, again, chlorine analyzer, temperature, pressure, pressure. And this is the north fill reservoir line with a flow meter. We've got two other flow meters to our pumps 1, 2, and 3 that will boost pressure into the other zones. We've got pumps 4, 5, and 6, which take water out of the reservoirs and will boost water into zone 2. We've got up here sodium hypochlorite. We dose hypo into the water for disinfection. This is the overflow storm sewer wiring and wet well. I think this is, yeah, this is being removed. And lots of engineering notes. Here's electrical, here's construction notes about chamber drains, plumbing. These are pavement and trenching details. Like I said, I showed you drawings last time. The other drawings were electrical and mechanical upgrades. These ones are doing new piping. So you can see here, all of these hash marks are P&IDs. These are removals. So they're ripping out old pumps. We're putting in new pumps. So for this project, it's a balancing act of the old PLCs being ripped out. But first, there's a new expansion to the building going up, a new MCC and a new electrical feed coming into the new MCC. Then we're going to decommission some old pumps. We're going to then put new pumps in their place after rebuilding their pump mounts. Then we're going to commission those pumps. Then we're going to turn off the other set of old pumps. We're going to put new pumps in, wire them all to the old MCC. Then we're going to move over some other systems, and then we're going to decommission the old MCC and rip it out and decommission the old PLC. So it's a huge project. So and its scope is different than the other one, but the drawings are all read similarly. So here's process and instrumentation. This one's showing removals. So you can see this is what's left of some of these systems. Here's our hydro. We got 13.8 coming into this facility. There's the site transformer, 13.8 to 600 hydrometer. Again, this one shows even less detail than the last drawing, which talked about pad mounted oil filled transformer, power monitors. We've got disconnects. Doesn't even list the sizing of these lines going out to those pumps because these ones are all being ripped out. We've got 600 volt here. We got 600, 400 amp after the ATS, a portable generator, well pumps, pump 1, pump 3, pump 4, pump 5. So this is an even less detailed one, but the information is still, we know where the devices are and what the voltages are coming to them. And later on, if we need to, we can dig through and find more information. And part of my job with this and the engineer's job is to look through and try to find and make sure that we catch all the details, that we make sure that the detail that tells them how big the pumps we need are there so that they can potentially size all the electrical protection equipment properly and bid on it. Here's construction information on it. Here's their legend for their mechanical. So we've got VFDs, we've got mixers, vacuum relief valves, four-way valves, solenoid valves. You can get the picture, I'm sure. And we get into piping layouts, so you can actually see where the pipe's going to go. Instruments. Do you have an instrument somewhere? Nope, not on these ones. Proposed new vertical turbine pumps. Hot water tank. Placeholder for blank sheets. P&ID drawings. So again, we've got more P&ID drawings, and you can see here Now we're using liberal use of those squigglies again that I was talking about. Zone 1 comes in, AIT1, 22 and a squiggly. Now we have to go play Where's Waldo and find 22. 22, we have chlorine analyzers. It's a free chlorine residual, which is an AI, and a fault, which is a DI. And we have 3 of those. So if we were to look through this drawing and go 22, 25, 44, we got 22, 25. I don't know where 44 is. Somewhere. 44. So we multiply that. We got 2 times 3. There's 6 IO points, or 3 DI and 3 AI. So if you were gonna start quoting and building a control panel based on these drawings, well, you could go through and go, oh, okay, well, you've got well pumps, horizontal booster pumps, and vertical turbine pumps, and they all have the same IO points. Well, and we got 8 of them. So we've got 1, 2, 3, 4, 1, 2, 3, 4, 5, 5 times 8 plus 1 times 8. So 16 AI, 8 AO, 8 DO, and 40 DI just for these pumps. And based on 16-point input cards, well, we need 3 digital input cards only for these pumps. And if you want to spread them all out, you're probably going to want to do 4, so you can do 2 per, so you can always have some available, or maybe you want to do 1 each plus. Sorry, I may be rambling, and I see people are dropping off, which I completely understand. This is a lot, and there's 0% chance that I'm going to catch everything in flying through some drawings with you guys. Yeah, please, if you have questions, let me know. More single line drawings. So this is where we're starting to get into more detail with the breaker layouts. These are actually coming in. It looks like Electra, who's the electrical supplier of the city. No, that's just North. Ignore me. 700 kVA transformer coming in. We've got our meter from Electra. That's who supplies us our power. Surge protection, a new ATS, the automatic transfer switch. Here you can see that instead of calling out on every single one of the lines what the wires are, they kind of have these little hexagons or pentagons, hexagons that detail how many conductors and how big they are for the different runs of wire. So these are, that's an 8 and that's a 6, 6 being 3 plus 1 conductor, number 10 AWG tech. Tech is a specific type of cable that comes with armoring around it. There's lots to know. Heaters, again, here's that symbol that is showing that kind of looks like a resistor. It's a heater, waste heater or room heater. We've got booster pumps, 20 horsepower, 40, 50, 150. Yeah, we're losing people. 13 minutes. How long can I talk? Here's an interesting layout of where all the instrumentation is going to go. So that's I mean, there's a good snapshot of just how many pieces of equipment there are in facilities. This is a medium complex booster station, and you're looking at what, 100 instruments, 8 pumps. This doesn't include door switches, chlorine equipment. There's a lot. There can be a lot. There can be very, very complicated control systems. And I think that is the last drawing. Yeah, looks like that was the last drawing. Neat. Yeah. This was a neat project. Again, I'm gonna go through this one very quickly, but just to show you the different scopes and scale of projects, you can see compact logics processor with a complex Cisco router and a secondary like it's called a Pribusen that transmits information over bell lines. There's your hydrometer, short single line. So we had a pole mounted transformer coming into a power meter. There was an ATS with a generator receptacle. This panel just sits on the side of the road and it runs 3 huge pumps underneath Dairy Road. So they built a kind of an underpass under the bridge on Dairy Road in Milton. I think it was Milton. And underneath it, there's a huge stormwater containment tank that these pumps will run. So after a rainstorm like today, 2 of these pumps are running full out, probably moving 175 liters per second of water from there just to keep it passable by cars. Surge protection equipment and a small lighting panel. This pumping station is required to be built without a building. So there's this huge double-sided 4-door stainless steel panel. On this side was the control, and on this side was the high voltage stuff. So you can see on the high voltage side, again, just like an MCC or like a building, you will have your main power will come into the meter. There's a manual transfer switch that would switch over to the generator when it was connected in. There's your main breaker. Here's your main surge protector. You'll notice the bubbles on these ones. Those numbers, in a perfect world, there's a bill of materials or a BOM. I'm sure everybody's heard BOM before. Those will line up with the different item numbers on this bill of material. So you can see that this panel, the bill of material for this control panel is massive. Really cool. It's probably my favorite panel I built. Very complicated electrically for such a small footprint. It had additional jumper panels inside of it. And then on the control side, we had here double inner, like an inner swing door, and we had the handoff auto and all the lighting control for the pumps, plus their automated backup system. So they ran on VFDs, but they also had starter backups in the event that their VFDs failed, and the PLC was behind that panel. So when the second one swung out, there was the PLC panel, and here was the storm panel pumping control. Like the backup control was in here. There's all your different terminal blocks. That layout you could see in the last drawing. This is the motor control panel. So you've got your main breakers, and you've got your soft starts. Sorry, this one doesn't have drives. It has soft starts, and then it has bypass contactors, not VFDs. Soft starts are similar to drives, but they only accelerate up to their speed. So they can't modulate their speed, but they will start slowly, which is better for the equipment. A bunch of internal panels, a networking panel. And then here we start getting into the control circuits. So here's the single line. We had the power coming in, lightning arrestor. There's the meter. There's a surge arrestor. Here's a manual transfer switch to the portable generator that you could connect to it. Come down into the main power splitter for the panel. Transformer, 600 volt down to 120. Then we jump right here into pump one soft starter with the bypass contactor, overload, it was a 11 kilowatt, 11.2 kilowatt pump, a couple of thermal leak contacts. So this drawing set gets more detailed than some because it was such a it's all of the equipment that could be in a building, but only in a single panel. So to keep the drawing set as slim as possible, Alan, the guy who built it, did, I think, a fairly good job. He had a heck of a time with the wire numbers because the client had their own specific way to label all of these things. So he had to follow their standards. So it's a little haphazard. And again, the wire numbers are only kind of predicated based on where you're moving in the panel. We had another, so here we have another step down transformer for this pump. A little unusual to have multiple step down transformers inside of a panel, but this one did. We've got our load center panel for like supplying power to different sections. It's really a lighting panel with circuit breakers. There was a air conditioner for this panel because it's stainless steel and it sits on the side of the road. These are the door contacts for lighting, for security system. If somebody were to break into this panel, they could do a lot of damage by shutting those pumps off. So that's alarmed. This is the control circuit for it. So you're showing here, this is actually a jumper. It's a loop of wire that you could actually see. You got e-stops up here. When the e-stop's pressed, you have a status for it, but it actually opens up power to prevent things from happening. So the e-stops have to be pulled out. Overload, soft start, pump temperature, and then CR1 for pump ready. So the pump can't be overloaded. None of these, so the soft start can't be faulted. If it is faulted, is it disabled? So you could disable, you could ignore that fault in the event that you had the system in bypass. You got your handoff auto switch for the pump. So local off remote or local remote is how they had it, with start and stop and start buttons, the seal-in circuit. Then you had your PLC run command and stop command. And then that circuit times 3 for all the different pumps. You have overheat sensors because these pumps are underwater. They have special flight mini cast monitoring relays that are wired in a specific way, which is captured in these drawings with their reset. More motor starter circuit, more motor starter circuit, lots of motor starter circuits. Lighting panel. So this is literally lighting. If the door opens, turn on lights. Surge suppressor, supplying power to the UPS, then there you go, 25. So circuit breaker 25,200 actually lines up with that line. So he did get some of the stuff in there. Awesome. So this is an example. He was able to do it. Oh my goodness. I'm sorry I said something incorrect earlier. So you'll notice here, if Hardik is gone, which is fine. I don't fault him for it at all. 25,120 power fail relay. I'm surprised you guys are still here. Thank you. So the UPS supplies power to the 24-volt power supply for the PLC. Then we have digital input modules, digital output modules, and power distribution, more power distribution for the network panel, power distribution for intrinsically safe relays, which are required when you wire floats from a sewage wet well into an electrical panel, you have to use equipment to electrically isolate it so you don't spark and cause an explosion. 24-volt power supply to step down to these contacts for the UPS. Down here, there's a specialty cable for the alarms on the UPS. The Siemens ultrasonic level control transmitter, how to wire its ultrasonic head, where to get its loss of echo, where to get its analog signal, and how to power it. Logix controller, PLC, IO. So there's your PLC, card 1, card 2, card 3, card 4, 5, DO, AI, AO. Where was the AO? There's no AO again, because they're not drives. Bill of materials and all the terminal blocks. Wow, I got through all those drawings. Cool. That is really all I've got. I don't have any more drawing sets for you. I hope you guys, that wasn't too fast. There's only 4 of you left. Any questions?